Thanks for the warm welcome. Can everybody hear me? Perfect. Where's the slider? Okay. So how does this work? Okay. So I want to apologize in advance. My talk is going to be way less visionary than most of the other talks you've heard before. It's going to be deep in the guts of machine learning. Dataset shift in machine learning. So why does this matter? So motivation, so this is Clark, he's a data scientist, and he just built a model to predict whether or not users are going to click on display advertisement, right? And so he's got happy with the results he got in his model assessment phase, and now he wants to put it into production, and the company is profiting by basically reducing customer churn by more targeted advertisements, right? So 3 months down the road, the company expanded into new regions, integrated new affiliates, and now Clark is asking himself, the data that I apply my models to looks quite different than the data that I've used to train my models, right? Are my model assessment results still valid, right? Do I need to retrain my model? And so what I want to do in this talk today is try to answer these kind of questions or give guidance on how we can answer these questions. Okay, I can skip that one. Agenda. I want to start with a quick introduction just to get us all on the same page. And then I structured the talk into 3 sections. First, I want to talk about dataset shift, what it is and why it matters if you're doing practical machine learning. Then I want to shift gears and talk a bit more practical. How can you identify if you're actually exposed to this problem? And last, I want to talk briefly about what you can do to correct dataset shift in case model retraining is not an option. And I do have some supporting material for this talk on my GitHub page. And also, this talk is heavily influenced by NIP's workshop. It's quite old already, but there's a compendium. So if you want to dig deeper into that, I suggest you dig into that. Good. So this talk is solely about supervised machine learning, right? And it's usually in supervised machine learning, we're given a set of examples. So those are basically pairs of x and y's. The x's are called our feature vectors, right? Those are vectorial descriptions for the objects for which we want to generate predictions for, right? And so if you want to do web page ranking, those vector coefficients could be, what's the similarity between your web page and your query, right? Or what's the page rank of the document that you want to rank, right? Or what's the freshness of the page in the index? And the response y is usually a real valued number, in which case we call it a regression problem. So you want to predict the price of a stock. Or it could be a mutually exclusive class label. So, spam or not spam, right? And you're also given this loss function that you can use to assess how well your model is making predictions, right? And the goal is to find a function that I call h here that basically maps from x to y, right? And you want to find a function that has minimal error on new unseen data, right? So this is the general problem of supervised machine learning. And we have many examples of this. Spam detection is one of them, credit risk scoring, numerous others, right? Now, how do we find this function h, right? And so there are many inductive principles that machine learning algorithms use to guide us in this quest, right? And these principles basically all postulate a number of assumptions, and given those assumptions hold, they can provide us an answer, right? And the most one fairly fundamental one is called empirical risk minimization, and glossing over many details, the answer that it can give us is basically pick the one that minimizes the error on the training data, right? Which seems sensible. But it has one key assumption that most machine learning techniques that we use these days, be it neural networks, be it gradient boosting machines, etc., have, which is training and test data need to be drawn IID from a distribution over our feature vectors and over our labels. So let's digest a bit what that actually means, right? So first of all, we need to submit to this idea that our data is generated by some stochastic process, right? So basically all the emails or your spam emails are generated by some probabilistic process. And then you can also sample from that process. And in particular, you sample from it, an IID stands for independently and identically distributed. The identical aspect means that the distribution that generates your data does not change over time. It stays fixed, right? And if you look at your email spam, you'll notice that the vocabulary in there changes over time, right? So this is commonly violated in practice. And also independence is basically, it boils down to the fact that you sample an example has no impact on the next example that you sample from that distribution. And that is also often violated in practice, right? Imagine you build an intrusion detection system that sits on a packet switch, and it screens incoming packages, whether or not they come from a denial service attack, right? Then usually the number of malicious packages overall is fairly small, right? But given an attack happens, the likelihood that the next package is malicious is highly affected by whether or not the given one is malicious, right? So in dataset shift, we basically fiddle with this fundamental assumption in machine learning, right? So we go from this classical view that training data and test data is drawn from this fixed but unknown distribution to a view where basically training data and test data are drawn from what I call here a source distribution and a target distribution. And then the question is whether or not learning is still possible in such an assumption, under such conditions, right? And arguably, if training and test distributions differ arbitrarily, right, then learning is not possible. So if the future is unlike than the past, or it has nothing in common with the past, then you can't learn, right? So we need to make some assumptions still in order to fuse these training and test distributions. So what we usually do is we factorize, you can see this here, this distribution into two aspects. One is called the conditional probability, which is basically a labeling function, right? Given a data point, what is the outcome? And this is what we're actually trying to model, right? This is our model. Once we have this, job's done. And the probability of seeing a given example, right? And so a classical case of dataset shift is what we call the covariate shift, right? Here we assume that these labeling functions are staying fixed between training and test, but actually the distribution, the data distribution changes over time, right? And so I've sketched this here real quick. This is an example that shows you a regression problem. You have a continuous output y on the y-axis and a continuous input x on the x-axis. And the ground truth, so the labeling function, is this senoid function, the wiggly curve you see here. And data points, you can see the bright ones are basically representing our training data points, so they are right-skewed, and the dark ones are left-skewed, right? And this is a classical example that happens often in medical testing, right, where you're subject to some sample selection bias, right? So often you end up having more training data from a certain subgroup of your strata of your population, right? Because, for example, older patients might be are more likely to get screened, and thus you end up with more training data for this. So why does this matter if you do machine learning? So I'll illustrate this with an example that I have also in my supporting material. It's actually a bouquet app, so shout out to Travis. It's a really great visualization library. So this one is the classical XOR problem in machine learning, right? So the goal here is to separate red dots from blue dots, right? And what you can see here on the left-hand side, so you can see this checkerboard structure, this XOR structure. And what changes between training, left-hand side, and testing, right-hand side, is the relative proportion of these points in this space, right? And you might be tempted to think that many machine learning techniques might not be affected by this, right? In fact, many of the learning algorithms we use, like neural networks and support vector machines, they're so-called discriminative methods. They try to directly approximate this labeling function, right? But the problem is, if you work in a domain, if you apply, let's say, a linear SVM to this data set here, right? You can see it does fairly okay on the training data, what you would expect, right? But the hypothesis space is, so a linear function is not enough to match this checkerboard structure, right? So the model has to make sacrifices, and it makes sacrifices, and when it makes sacrifices, the data distribution does matter, right? So in fact, you can make this model arbitrarily bad on the test data, right? So basically, if you do machine learning, you are affected by covariate shift. Doesn't matter what you do. The counterintuitive thing is that actually, if you choose a more capable hypothesis class, so here this is a nonlinear support vector machine where you can model complex interactions in your data. You see that this adaptation loss actually drops, right? And this is counterintuitive because you might think actually that given you know that your data distribution changes, you might be tempted to use a more biased model even, right? So again, this should not mean that you should, in this case, you should use more complex models because again, if you use those, you are more exposed to overfitting. But it is counterintuitive, and it shows you that you're actually adversely affected by this. There are also other cases of dataset shift that are often intentional, right? That we actually do deliberately. One of them is imbalanced datasets, and many of you have done large-scale machine learning might have done this, right? In display advertising, it's a canonical example for this. You often end up with much, much more data for your majority class. 1 out of 1,000 display advertising events is actually a click event, right? And so you should subsample the majority class. And so if you do this, you're actually creating a dataset shift. The good story is that it's fairly easy to correct it as well. So in case you're doing this, and if you're using probabilities for your classifiers, please don't forget to recalibrate those probabilities, because otherwise they are simply wrong. So if you do this, I strongly advise you to look into this paper by Facebook engineers. I have it in the appendix. It's a really good example of large-scale practical machine learning. Another example was mentioned by Sayan earlier today is what's called domain adaptation, right? This is very common in natural language processing, where you often deal with resource-rich source domains, right? Usually English language, and resource-poor target domains, maybe Estonian, right? And the canonical example here is, again, sentiment classification. You want to build a sentiment classifier for political or financial news, but you're only given, but you hardly have any training data there, right? But you have ample supply of training data in other domains, like product reviews, scraped from Amazon. And so this is closely linked to a concept called transfer learning. Unfortunately, we don't have much time to go into this today. So let's shift gears a bit. Let's talk more practical, how we can actually identify if we're exposed to dataset shift. And so what I want to present here is basically a taxonomy of methods you can use to detect whether or not that's a problem for you. And you basically have two options, supervised methods or unsupervised methods. So I want to focus here on unsupervised methods because, in my point of view, they're a bit more practical. But basically what supervised methods mean is that with some delay, you usually get feedback on whether or not your predictions were actually accurate, right? And this could come delayed, and then you can keep track of progressive error, right? Or it could mean that at times you need to take away some resources, some people to actually label new data, and then you can run again model assessment, right? But the problem here is that the latency can be huge, right? So it might take you weeks or months to determine whether a model is actually not accurate anymore, right? So what I want to focus on is the unsupervised aspects, and I want to talk about statistically distance, novelty detection, and discriminative distance, so 3 methods you could use in certain situations. Okay, so statistical distance, it's very simple. Basically change detection using histograms, right? And so what you want to do here is you want to detect whether or not your model predictions actually change over time, and at the same time also, if that happens, check if your most important features change over time, right? And you can do this by simply just creating histograms of your most important inputs and of your outputs, right? And it's fairly easy to do. It's widely applicable. And also very easy to spot what changed. So what you do is basically you form a histogram of your training data, of your holdout data, and when you apply your model in production, you keep track of these histograms over time, right? And you basically just compare them. And what you usually do is you don't use visual comparison, but you actually summarize them into a number, right? So you can use something like population stability index, PSI, coupled live divergency, or KS statistic, to just summarize that into one number. So where is this used, right? So that's actually used heavily today in risk management. So many financial institutions, especially in the US, they require their modelers to actually publish population stability indexes for their credit scoring models. I was told that even governmental regulators might inquire those values. And usually a PSI value above 0.25 is deemed as a major shift, and you actually should retrain your model or phase out your model. And the other example that's extremely relevant for me is actually there was a fairly influential paper in 2014 from Google engineers on technical depth in machine learning systems. Basically, they proposed a system to detect prediction bias that uses these histograms to detect changes in the predicted probabilities of your classification models, or the regression values of your regression model. And basically, in the future, we will see more and more components that are basically written by software components that are written by machine learning, right? And we have, obviously, they are part of a bigger system, a bigger software system that, unfortunately, we end up with the situation that we have a lot of a tight coupling between upstream components, usually those components that generate features, right, and our models, right? And it's really hard to detect this when changes happen using just end-to-end testing, right? You actually need to monitor this in a live system. And you can do that. A good story is you can do that fairly easily using existing systems monitoring, right? So I sketched out here a reference architecture for this change monitoring for predictive models. Basically, on the left-hand side, you have your model service layer. Think of your JPML models deployed in some Jetty service container. And then you basically offload predictions and input data into a message bus, and you take these and index into some kind of time series database. So if used in the past, Graphite, you can use influx data, you can use timescale DB, and then you can use open source tools to basically visualize those histograms. And the good thing is usually you have your application metrics of your system already integrated into this. So you know when you deploy your system, when changes might happen, etc. So fairly easy to do. I think I've seen this now, more and more people adopting this kind of approach. Good. Another method you can use to detect a shift that's more amenable to fairly complex domains, domains like computer vision, audio, remote sensing, is novelty detection. So basically the idea here is that you create a model to model this source distribution, right? And then given a new data point, you try to test whether or not, what is the likelihood that this data point is drawn from this source distribution. And you can use various density estimation techniques for this. And here on the right-hand side, I show you an example using what is called a one-class support vector machine. Those methods are available in most common libraries and software packages. And Scikitlearn has a very good implementation based on libsvm for this. And again, like this works primarily, if you are in this regime of homogeneous but very complex interactions, then this is definitely a method you should look into. And histogram-based methods are just not a good fit for this. The disadvantage here is that you actually can't tell really what changed, right? It's kind of difficult with such an approach. A third approach that is less used in practice, but I've been seeing this being used in Kaggle competitions quite a bit, is what's called a discriminative distance, right? Here, basically the intuition is that you want to train a classifier to detect whether or not an example is from the source or from the target domain, right? And you can use the training error to basically as a proxy of a distance between those two distributions, right? So the higher the error, the closer they are, right? And so this is widely applicable. You can apply that to high-dimensional sparse data problems. You can also use, if you use a logistic regression model to classify between training and test, you can also use the weights and the factor loadings as kind of a feature importance metric, and you can pin down to actually what changed. The disadvantage is that that's usually an offline procedure, so it takes a while, and it's also fairly complicated to do. But this is a very promising, effective technique also if you do something that's called domain adaptation, what we mentioned before. So if you want to figure out which language is closest to Estonian, you can use such an approach to identify, out of a catalog of different domains, which one is the ones that you actually want to use for adaptation. Good. How we can correct dataset shift? The short answer here is you don't, right? You retrain. So if possible, you should always retrain. In some situations, it might not be possible. So if there are latency problems with retraining, or you're actually deliberately doing this, right? Then I just want to show you two easy techniques you can do to correct the dataset shift. So one of them is called importance reweighting. And the main idea is you want to upweight training instances that are very similar to your test instances. So basically what this amounts to is you try to change your training data set such that it looks like it was drawn from the test data set. And so the only thing it requires is you need unlabeled examples from the test domain, right? Which is usually something you can get fairly easily, right? And there are different methods on how you obtain those weights. And here are just an example that I show you using this discriminative approach that we've talked about before, right? So what I show you here is on the left-hand side, you see the training distribution, right? It's just uniformly distributed over this checkerboards structure. And the test distribution here, you can see there are way more data points in the northern hemisphere, right? So if you train a classifier to separate, you just ignore the color for now, to just separate left from right, that classifier would most likely cut through horizontally, right? And conversely, you can use the predictions of that classifier, the probabilities, to weight examples. So examples that are more likely to be drawn from test distribution, you upweight those examples, and examples that are less likely to be drawn from test distribution, you just downweight those examples. And this is a fairly easy approach. You can do that super easy in Scikit-learn, a couple of lines of code. You just need, a couple of, basically, your data from the source domain, your training data. You need unlabeled data from the target domain. You create your pseudo labels, You just label the training data sets negative, test data sets positive. You train a model on it, and you take those predictions of that model and plug them in. Most estimators in Scikit-Learn support this weight argument, and then you run predictions. So it's fairly simple. If you want to learn a bit more about it, here's a blog post by Alex Smoller that I think the slides will be distributed later. You should look into that. It's a fairly simple technique, and I've seen people use that also quite successfully in Kaggle competitions. Right. The last approach here, just very quick, is what you can also do is you can actually change the representation of your data in order to make it appear more like that the two distributions appear more similar. And given that you can still make good predictions on the training data, right? So you do fairly well on the training data. That means that this mapping will help you doing knowledge transfer, right? And a very simple example of this is feature selection, right? So if you do feature selection, so just intuitively, a feature that differs a lot between training and test, right? But does not give you a lot of predictive power, you should just drop that, right? And that's one of the key lessons in a lot of these Kaggle competitions is that you should be doing this, right? So this cost me a couple of months of my life and potentially a promising Kaggle competition once. So I strongly suggest looking into this if you want to compete on Kaggle. Good. So to summarize, supervised machine learning techniques are negatively affected by dataset shift. So this is relevant for you if you do this. Good story is there are some simple techniques you can use to detect this, and especially histogram-based methods. I strongly suggest you look into this. There are other methods that work well in certain scenarios. Again, you can correct dataset shift, but this is only if you don't have the potential to actually do retrain. And discriminative rewriting is a very simple and effective technique to actually do this. So yeah, I think I'm pretty much out of time. No? It says 5 minutes. Okay. I think I open up for questions.
Let's take the questions. Is there any practical solution for the situation where the dataset shift occurs significantly faster than actual model performance can be measured on live data?
The model performance can be measured on live data. That's a good question. So I mean, these unsupervised methods that are presented here, right? So you don't need to know what the model performance is, right? There are methods in machine learning that use online updates, right? So these kind of online methods in machine learning. I have to admit, they make fairly different assumptions than the ones I presented here. So these assumptions that are presented here are usually for these classical machine learning methods that most of us, or most people, I would say, use, right? And so those are the only ones for retraining I can offer. Yeah.
Thanks. And what about the detection of dataset shift for unsupervised learning?
Okay, that's interesting. Detection of dataset shift in unsupervised machine learning. Many of these techniques that I mentioned with the unsupervised methods I mentioned to predict data, to identify dataset shift can also be applied to the unsupervised case, right? So they are all applicable to that case.
Is it possible to use machine learning to estimate and adjust for dataset shift?
Can you repeat that?
I'm not the one asking the question, so maybe someone can clarify. Is it possible to use machine learning to estimate and adjust for dataset shift?
Yeah, absolutely. I mean, here I presented 2 examples at the end of my talk. Those are 2 examples. There are many more, but I think it's something that's not done very commonly. So.
But the question was asked after your presentation, so maybe whoever asked.
Okay, we can clarify. There are definitely many more techniques out there, and it's an active area of research as well. I try to stick to the practical ones.
Thank you.